the Visual Cam plugin automatically load in SOLIDWORKS. You'll see that there is a Visual Cam tab under the Command Manager in SOLIDWORKS, and you'll also see the CAM interface, the machining browser interface, show up in SOLIDWORKS. So you can switch between your Feature Manager design tree and Visual Cam by just a single click of a button. So we have the machining browser over here on the top half of the browser window, and then the machining objects browser is on the lower half. So the tools, machining regions, and features tab, these tabs allow you to define tools. You can also load tools from your library if you already have defined one, or you can create tools and save them to a library. You can also establish properties for the tool and the feet and speed, and these can be also determined based on the material you're working with. So depending on the stock and the tool material type, there's a built-in feet and speeds calculator that will help you recommend your feet and speeds in here as well. Now I'm going to go ahead and start with an example where we can program a 2.5-axis toolpath, and then from the next step we'll take a look at how we can program 3-axis as well. Would that be good?
Yep.
All right, great. Now, at any point during the demo, if you do have any questions, feel free to, ask me those questions, and I'll try to do my best to answer them for you. So you're more than welcome to interrupt me during the demo. So first step, what I'm going to do is load a prismatic part that was modeled in SOLIDWORKS. Now, you could be working with files that have been designed in SOLIDWORKS, or you could be working in files that have been imported into SOLIDWORKS as well. So once you bring in a part in here, the first step in the programming workflow is you'd want to define the machine tool setup. So in this step, you're going to define the orientation for machining the part. So now the part could be programmed, designed in any orientation. So typically, the XY plane in SOLIDWORKS is the front plane, but designers tend to use the top plane or the right plane to start designing the part. So no matter what plane that you use in SOLIDWORKS to design the part, you can use these controls in here to orient the coordinate system. You can use select a face, select a planar curve, basically it's a planar sketch. You could pick an active plane, or you can use these controls in here to reorient your coordinate system. So you can change the orientation of the coordinate system to establish your X, Y, and the Z axis orientation. Now once you establish the orientation, the next step is to define the type of machining process, whether you're going to be doing 2 and 3 axis, 4 axis, or you want to do 5 axis programming. So we have different configurations of the mill module, starting with standard, expert, professional, and premium. And the professional offers you advanced 3D milling methods that are more geared towards tool and die making, mold making. Our standard configuration does offer 2 and some of the 3-axis toolpath methods as well. The expert configuration would be ideal for for basic 3D milling plus doing a rotary 4-axis milling. The professional includes 2 3-axis, also includes 4-axis, and also programming from multiple orientations, which is known as 3+2 machining, or it could be also called as indexed 5-axis machining if you have a 5-axis machine tool. So in here, I'm going to set the number of axes to be 3, and then I'll select OK. The next step is to select the post-processor. This would be the machine tool that you're going to be writing out your G-code for, and you mentioned to me during the call that you're using the Haas machine. So I'm going to pick Haas as the post-processor and set the output file extension as .nc. The next step is we want to build the stock material that would be the workpiece. So you would pick stock, and you can select the type of stock you'd like to create. So you could be starting with a rectangular block, so you would pick box stock. And in this particular process, you'd want to establish your length, width, and the height. By default, Visual Cam will detect the bounding extents of the part and tell you the minimum size of stock material that you would be needing to be able to machine this part. You can also change the parameters in here, so you could be working with a stock that's 6 by 5. If you need to change the height or the thickness of the material you're going to be starting with, you can modify the settings in here. So once you establish this, you pick OK, and you can click on Show Stock Visibility, and that'll display the stock right on top of the part. Would there be any questions so far, gentlemen?
No.
So as you're noticing here, I'm working through each of these groups, working my left to right. So I define the machining process, machine tool setup. The next step is I'm defining the stock. In the next step, I would like to align the stock to the parts. I'm going to pick align and set the Z alignment to be at the top and then the XY to be centered. And now I'm going to pick OK. So you'll notice that the stock is now being centered around the part in X and Y. In the next step, I'm going to select the material I'm going to be working with. So it could be aluminum, you could be working with tool steel, you could specify the type of material in here. I'm going to pick aluminum 6061 for the purpose of today's demonstration, accept it. And when I click on material texture visibility, it actually applies the texture of the aluminum that's displayed in here in the texture to the stock material. So this is something you can use it for purpose of simulation, selecting the material, and also for defining your tools. So as you go define your tools, you can use them for establishing your feeds and speeds. And then we would want to establish the work zero. So as you place this piece of material on your CNC table, you would probably want to establish your work coordinate offset, or also known as like a G54, to probably one of the corners of the box, which is typically common, or you can even put it in the top center, dead center of the part as well. So that can be done using what's called work zero, and you can pick set to stock. You choose the zero face. In this particular case, I want to put the highest Z. I'll pick southwest. So this basically establishes your XYZ origin for the stock. And you can output this as your G54, you can set that, or if you're using a different work offset number, you can specify it right in here. Would there be any questions so far?
None.
Okay, great. So we're now ready to program some tool paths in here. So first step, I would like to go ahead and pocket these holes. I'm going to go to 2-axis. You'll see that there are several different types of methods offered in 2-axis. You have roughing, facing, pocketing, profiling, V-carve roughing, V-carving, engraving, slotting, chamfer, hole pocketing, hole profiling, thread milling, T-slotting, and remachining. Now, all of these methods are offered in the Pro and Premium configurations. If you look under the methods for 3-axis, the 3-axis advanced module, which is starting with the Pro, offers all of these advanced 3D toolpath methods. And 4-axis is included with the Pro configuration, plus you have hole machining. Now, the simultaneous 5-axis methods are not part of the Pro configuration. So first step is to do a pocket. So we're going to go to 2-axis and select pocketing. Now this displays the pocketing operation dialog, and you work your way left to right as you work through each of these tabs in here. So first step is to select the areas to pocket. So I'm going to use part regions, and I can just right-click on the edge and select tangency, or I can use select loop. So you can take advantage of your SOLIDWORKS selection tools in here to make your selections. So once you have the object's geometry selected, you accept your selections. Next step is to make a selection for the tool. I have a 1/4" end mill in here. If I'd like to modify or make changes to it, I can always edit all of these parameters in here. Go to feeds and speeds. You'll notice that the feeds and speeds are being loaded from the tool. You can establish your clearance, which is basically your safety plane for your transfer motions as you transfer from one pocket to the other next pocket. You specify your cutting parameters where you can set the tolerances for pocketing, set your stock allowance if you want to leave any side stock or wall stock, so then you want to go back and do a profile pass to clean it up. You can specify a stock, or if you want to just do a finish in one operation, you can set the stock to 0. You can pick from one of these cut patterns in here, set your step over distances. Under cut levels, you can actually pick the depth. I can just pick the top face and then the floor. It establishes the depth as a 1/4". You can specify whether you want to break it into multiple steps. You can do it in 2 levels. You can set your entry and exit, any additional parameters like for fitting arcs to your tool paths, and you can also sort them, the pocket sequence, and then pick generate. So this creates your pocketing toolpath. The toolpath is previewed on top of the part. You can also watch the toolpath as you step through each level. Now I'm going to go from the Program tab over to the Simulate tab, select the machining operation, and click on Play to run the verification. You can always toggle the display of the toolpath on or off. You can also speed up the simulation. So this is a typical way of how you would program these parts by selecting, boundaries, or you can select face edges or sketches to define the areas for machining. And then you want to do these holes in here. You can identify the size there, like 0.4 inch. So I can probably profile these holes, or you can pre-drill and then machine those holes. In this step, I'm going to do a hole profiling operation and just select these two holes in here. And I can specify the same cutter, specify the properties in here. I can specify the depth by just picking the top edge and then the bottom edge. So you can do top face and the bottom edge. You can specify all these parameters, specify the parameters for like the helical pitch. Entry and exit can be set right in here, and then generate will result in the hole profiling toolpath. So notice that the toolpath creates a helical pattern, and then down at the bottom, I can add a finish pass. So it'll basically do a cleanup pass down at the bottom of the hole as you get to the bottom of the hole. So you can run a verification by selecting Simulate. So the finish pass is added at the bottom of the hole. And finally, you want to do a profile cut to relieve the material. You go to 2-axis, select Profiling, and I can right-click on this and pick Select Loop. It picks the entire loop around the part. Specify the properties. You can choose to determine site to cut based off the 3D model. Use the midpoint of the longest site for the location of entry and exit. You can enter in the depth in here. You can specify multiple depths per cut. Set your entry and exit parameters, and then generate. And there's your profile toolpath. You can run a verification. You can also add bridges and tabs. So now in this particular step, what you noticed was we are programming each and every operation by selecting the boundaries around the part, like profiles and pockets. Now what we've introduced in our latest version, which is 2017, is feature detection and machining. So when you have parts like these, prismatic parts, rather than having to go through these process of selecting edges around the part, you could actually detect features from the model. So I can use create machining features. I just pick that face right in here, accept it. So this will go through the process of identifying the features. So you'll now notice that we have a planar face. We have these prismatic pockets in here. It also treats this as a pocket. And you can see that there's hole features being identified. There's 2 hole features and the 3rd hole feature right in here. So rather than having to program each of these as separate operations by selecting those features, you could actually select from the feature, right-click and program a toolpath. I could do a pocket operation in here and just grab the cutter. You'll notice that all the depth information is automatically determined from the feature. So all I'm going to do is change my depth per cut and then select Generate. So you can take advantage of feature detection and machining. So I could do the same thing for the whole feature in here, hole profiling, and you'll notice that the depth and all the properties are automatically obtained from the feature itself. And you can generate the toolpath. Any questions?
Does this give an estimated machine time?
Absolutely, it would. So let me go ahead and just clear these 2 operations out. Right-click on the setup. I go to Information, and based on the parameters that you put in, it gives you an estimate of the machining time for each operation and the total cutting time. Would that help?
Yep.
Okay. Now, we've also added a lot of nice features in here where you can establish for simulation, you can apply different types of colors. You could say for the pocket operation, you want to use a different color, and for the profile operation, you want to identify those features using different colors. So it's easier to identify what material is being removed from each operation in here. So I can pick different colors for the simulation, and I can set by applying based on the operations. And now you'll notice that it applies different colors as you program each of these operations. The simulation can also highlight the edge of the cut material during simulation as well. So there's a setting to make that visible as well. Now, since I left out one of these holes in here, I can go back and add a toolpath for those as well. So I can select the operation, program a pocket operation in here, select this curve boundary, select that, and I can go to the depth in here, pick the top face and then the bottom edge, program the toolpath. I can reorder the operation in here so I can put it before the profile operation. So now I can go ahead and run a verification and then verification of the final profile cut. Now once you have all of these operations programmed, you could actually post-process this out to your machine. So right-click on it and then pick Post and specify a name and select Post. This will automatically post-process the code and preview it in a notepad. You can see your work offset numbers being output, and there's your G-code output for each of the operations. Now if you're using multiple tools, each of the tool numbers would be output, so the machine will automatically pause and prompt the operator to change tool if it's a manual tool changer, or if you have an automatic tool changer, it'll just go grab the other tool. Now we also have machine tool simulation that's available in our Pro configuration of the product, so I can go ahead and select a type of machine tool. So we have different machine tools in here. So for example, let's say I want to pick a standard VF3, Haas VF3 machine tool in here. I pick that and I select OK. It displays the machine tool. I can go to the machine tool simulation in here, and I can select the operation and then click play, and that shows the simulation with the machine tool. Are you able to watch the machine tool simulation in here, sir?
Yeah.
So basically it shows material removal with the machine tool simulation active. Now we can also add additional machine tools in here, so you can basically have your VF6 model added to it. So it's basically for visualization purposes to make sure where how it's cutting on the machine. I'm going to hit pause to pause the simulation in here. And if you want to switch the machine tool simulation off, you can just click on this toggle in here, and that'll toggle the visibility off of the machine tool. Now, one of the nice things I like about being able to generate what is called a setup information sheet, so that can be done using what's called shop documentation. So you can basically right-click on the setup and then choose shop documentation, and you can pick a folder where you want to save this out. So this basically creates a setup information sheet, which is very useful for the the machinists in the shop floor to learn more about what's exactly being machined in here. So if you're not going to be the person who's going to be also operating the CNC machine tool, so this gives information about the part that's being machined, also provides information on the tool, and a list of machining operations. There's also a detailed setup sheet that you can generate, which will have screen captures of each and every operation in here. What I output is using one of the templates, so templates can also be customized. And if you're familiar with HTML programming, you can modify these layouts in here and stuff like that. Okay? Saving the part in SOLIDWORKS will automatically save all of the machining operations what you programmed into the same SOLIDWORKS part file. So we're not adding any additional file types. Only the additional file that you're typically generating is your G-code output file, which you need to transfer it out to the machine. You can also save these operations that you program to a knowledge base. So when you have parts that have a similar workflow or family of parts where you like to utilize these operations, you can load them from a knowledge base to program it. Would there be any questions before we take a look at a 3D example?
So you have both a manual programming method, and then the one on the lower left is like an automatic. Then where you didn't run the post on that, but you program this both a manual way and an automatic way.
Right. So what I showed you was one of the ways of programming is by being able to select the boundaries in here and program. That would be, I would call it a traditional way of programming it, right? You pick the boundaries for pocket. Now, we also have what is called feature detection and machining. So you could actually, identify features, which we did by basically picking the face on this part in here. And now once you have those features identified, you could program these features, right-click, and I could choose pocketing. So you don't have to go and pick each of these edges on the model. Once you identify the features, you just define a tool and program the toolpaths in here.
Okay, yeah. So you just didn't post that part, but you could post that automatic method there.
Absolutely. I could do that as well, and I'm going to show that to you here in just a moment. So I have these programmed. I'm going to go ahead and create a, you can see that it shows the cross-section of the hole. And first step I could say is I want to do a hole pocket, and I can go all the way down to this first step. And then I can also add a secondary operation in here for the hole pocket. And I can specify the toolpath, or I can just do a drill operation in here for the second step in here. So basically, you can specify each of these parameters. It'll create an operation set. I can right-click and regenerate. So there's the toolpath for each of these steps, as you notice it. So now we can go ahead and simulate all of these. You can do simulate until. That'll simulate through each of these operations in here for us. And once it's simulated, we can go ahead and post-process these to the machine as well. Right-click and post. And I'm just reposting it. It's outputting it right here. Yeah, so you could be using detect features and machine it, so feature detection and machining, or you could be using, the conventional. There are certain type of parts you could use feature detection and machining, like parts like these, like prismatic parts. If the parts have multiple levels or multiple steps, you may have to do a combination of both feature detection machining and, identifying boundaries and selecting them as well.